Okay, great. Welcome back. So we'll start with Sam Garratt from Berkeley, who will tell us about quantum classical correlation, cross-correlation.
Thanks for the introduction. Thanks for coming to the talk. So yeah, I'm going to be talking about what we've been up to for the last year or so. This has been work in collaboration with Zach Weinstein, a PhD student here, and Ehud, and is written about in these two papers. So this is a talk that's in some sense about the limitations of what we can do with quantum computers in physics experiments. So the basic question is going to be whether we can observe the effects that lots of measurements have on a quantum system. And this has interesting connections, as I'll discuss, to problems in random circuit sampling. So, of course, the reason we're here is because we have some new platforms to play with. We have, superconducting quantum computers. We have maybe slightly more traditional quantum simulators based on optical lattices. And yeah, the feature that we have access to in these systems that I'll be focusing on is that we now have fine control over the measurement process. And so the question is, what can we do with this? So, of course, a strong motivation for developing fine control over the measurement process is that it's going to be necessary for error correction. In the many-body physics context, this control has recently allowed some pretty amazing experiments on the preparation of many-body topological states, which has required measurements and then conditional unitary operations performed after them. So I'm going to be talking about measurements not necessarily with the goal of creating a particular state or performing a particular computation, but just the basic effects that measurements can have on a many-body quantum state. So one context in which this problem has arisen is random circuit sampling. So I probably don't need to tell any of you about the details of the Google experiment from a few years ago where they declared quantum supremacy. So the problem here was to take some array of qubits, evolve them under some unitary circuit, and then having evolved them to measure all of the qubits. And then the point is that for a sufficiently deep circuit, it's very hard to sample this distribution of measurement outcomes on a classical computer. So it turns out that this random circuit sampling problem, or the hardness of random circuit sampling, is dual to what appears to be a quite different problem, which I'll illustrate with a very similar image to highlight the connection. And this problem is related to what we call the measurement-induced entanglement transition. So the measurement-induced entanglement transition doesn't involve measuring all of the qubits. You ask a slightly different question. You ask, okay, given that I've prepared some complicated many-body state with my unitary circuit, and I've measured maybe all of the qubit, this is one particular probe you can use, you could then ask, given that I've measured all of these qubits, except maybe two of them, can you tell me about the effect that these measurements have had on the unmeasured qubits? So you'd be interested not in measuring all of the qubits, but measuring, say, all but two, and trying to say something about the properties of this post-measurement density matrix. So this rho m indicates that the density matrix of this qubit is conditioned on these earlier outcomes. So in the context of random circuit sampling, it was shown a few years ago now, although the PR actually appeared quite recently, in this context, the sampling from this distribution becomes hard beyond some critical depth of your circuit. So this transition in the hardness of sampling is in fact dual to the statement that the post-measurement density matrix here is entangled with the other, this qubit here is entangled with the other unmeasured qubit. So in this context, it was referred to as a teleportation transition. So what I'm going to be, so on this hand, on this side, you say, well, okay, there's some quantum advantage in sampling once you get beyond some critical depth. On this side, actually, it'll turn out that if you play instead the game of trying to study the effect of measurements on this density matrix, you run into a problem that we call the postelection problem. So, okay, this brief outline of this talk is going to be, I'll talk a bit about what the postelection problem is. I'll talk about how you can mitigate it by rethinking the way you do the experiment, and then I'll talk about some applications of the scheme I describe. Okay, so the game is, how do we say something about rho m? So let's say we performed m measurements. So m in this case would maybe be n minus 2, where n is the number of qubits. When we perform these measurements, we get some string of outcomes. So normally when we do an experiment, when we want to characterize a quantum state, what we do is we measure an observable. So a standard way to characterize a quantum state is, of course, using an expectation value. So in this context, you might say, okay, well, I should prepare rho m, I should measure rho m, I'll get some eigenvalue of the Pauli Z operator, and then as we do in all standard experiments, we should just average this result. The problem is that we can't do this. The reason we can't do this is that in order to determine a conditional expectation value like this, in order to say something about the states you create through measurement, you have to prepare that state multiple times. But of course, if rho m was prepared by a large number of measurements, the probability that you end up preparing this state again is exponentially smaller than the system size. So you quickly find yourself in a situation where it's just impossible to characterize these post-measurement states by any standard means. A kind of aside for the computer scientists in the audience, so the post-election problem is it's a problem for experimental physics, but it's hinting towards a kind of fundamental limitation of what we can and can't do with quantum computers. So the point here, the point of these two papers, was to show that if you could force the measurement outcomes you wanted, if you could post-select for particular measurement outcomes, quantum computers would in fact be much more powerful. Turning that around, we can say that the randomness of the quantum measurement process, when we're trying to study a many-body quantum state, or when we're trying to design an algorithm, is actually a fundamental limitation. So so the question I'm going to be addressing is, given the randomness of the measurement outcomes, given that we cannot choose the outcome that nature gives us, how can we characterize the post-measurement states? So let's think about some toy example that we're all familiar with. So let's say that we have two experimentalists, Alice and Bob, and they share a bell pair, like up, up, plus down, down. So one of our experimentalists, Alice, measures their spin. Let's say Alice finds up. At this stage, Bob does not know the state of his spin. Bob's qubit is in a maximally mixed state as far as he's concerned. But now if Alice tells Bob the outcome, say by sending a postcard with the outcome listed on it, Bob, given this classical information, knows the state of his qubit. Another way of saying this is that provided Bob uses Alice's measurement outcome, Bob knows the outcome that his measurement will have with certainty. So this is just telling us that in an experiment studying the effects of measurements, you have to use the measurement outcome somehow. So okay, what do we do? So we prepare our state of interest through using a quantum circuit. Maybe it's a ground state. There are many different possibilities here. I'm drawing a circuit to make it look more familiar. So in each run of the experiment, which I'll label R, what we do is we observe some set of outcomes. We're never going to see this set of outcomes again. The probability that we see this set of outcomes again is exponentially smaller than the system size, or in the number of measurements performed. So in doing this, we've created our post-measurement state. And then we measure this state. We measure this state, we find some outcome, we call this outcome ZR, plus or minus 1, just one of the eigenvalues of the observable that we chose to measure. So the question then is, okay, as we're used to in experiments, we're going to have to do some kind of average. So the question is, given these results, which you'd hope were telling us something about the effects that the measurements have had on the quantum state, should we just average them? And the point isn't that no, we can't just average them. The reason we can't average them is that averaging the result of our experiment, this Z, has essentially the effect of converting our measurement outcomes into dephasing events. Like performing a measurement and not using the outcome is equivalent to a dephasing event. So one way of thinking about this is just by unwrapping this simple thing ZR. So ZR, which is plus or minus 1, we can think of this as the expectation value that we'd want, but which we can't get because of the need to post-select. We can think of it as this expectation value we want plus some noise, which is mean 0. Now, when we perform this average, what we're doing is we're washing out this noise as we wanted to, but the problem is we're also losing information on the variations of this expectation value over the ensemble of measurement outcomes. So we're losing the information that we wanted to get at the same time as washing out the fluctuations we wanted to remove. So a way to preserve this information, well, there's a lot of freedom here. A way to preserve this information is to just say, well, each run of the experiment, what I'll do is I'll take this number ZR, I'll pick another number, WMR. I'm not going to tell you what WMR is yet. So I just pick some number and I perform this weighted average. So this weighted average is now in principle sensitive to the conditional expectation values of the Pauli Z operator that I could use to characterize the effects of measurements. So if we do this, you indeed get away from this, in some sense you get away from the post-selection problem. If you demand that the variance of this object that you're averaging is a worst polynomial in M, you can now do your experiment in a time that is polynomial in the number of measurements you perform. But the problem is there's quite a lot of freedom here. So if you're coming at this from the perspective of wanting to do an experiment and study the effect the measurements have on a state, so far what I've told you is you should just pick a number. Pick a number WMR, and this should get away from the post-selection problem. The problem is that there's no longer a post-selection problem. There's no longer a barrier to looking for structure in the ensemble of post-measurement states. But the result you've got clearly doesn't have much to do with the quantum state. It depends very sensitively on these weights you've chosen. So what I'm saying here is that we just have too much freedom. So just reviewing what I was just saying, we have some weights, we have some outcomes, we average. When we average, we get rid of these fluctuations, we're left with this. So the question is really, if we want to study the effects of measurements, we have to choose a nice way to use the data. So one possible choice, which I'll deviate from in a moment, but at least the choice we settled on last summer, was to say, okay, what if we choose these weights to be our theoretical estimates for what these post-measurement expectation values should be? So this now gets you to a situation that's not too unlike cross-entropy benchmarking in the context of random circuit sampling, with the caveat that these are local objects. So if we choose our weights in this way, then instead of some completely arbitrary weighted average of our experimental data, what we end up with is the cross-correlation between theory and experiment. So this is what's observable. So this cross-correlation, which we call the quantum classical cross-correlation, is an observable signature of the effects of measurement. And I should add that this is not all a fantasy. This kind of scheme was actually developed independently and then implemented in this experiment by Google back in March, where they studied measurement-induced criticality. And of course, what you could do, you could take this cross-correlation between your expectation and what the experiment's actually giving you, and you could compare that with just your theoretical estimate, or the classical cross-correlation. Okay, so the kind of experiment that I'm describing here now is you take your quantum simulator, you perform your measurements, you get your post-measurement density matrix, and you measure this. You feed these measurement outcomes into a classical computer, here represented by this abacus. From the abacus, you extract your post-measurement expectation value, your classical estimate for the post-measurement expectation value. This could be any kind of classical simulation. It could be tensor networks. It could be quantum Monte Carlo if you're looking at ground states. It could be a free fermion simulation. You combine these two things, and this gives you your quantum classical cross-correlation, and of course also the classical object. Okay, so this is kind of where we were a few months ago now. I should add that this scheme only requires classical post-processing, so this is a realistic experiment you can perform without having any adaptive elements in your quantum circuit. But of course, the problem that I've hinted at already is that the way we construct these cross-correlations is completely arbitrary. And kind of another way of saying this is that our experimental result is sensitive to our theory. So in what sense can we call this setup a probe of our post-measurement quantum states? If we change the way we simulate the system, we change our result. And in this sense, you could massage your theory to get a better experimental result. And this is not an ideal situation. So, okay, what the first half of this talk is really about is, can we learn something about theory-independent quantities? Can we learn something about the effects that measurements have on a quantum system without corrupting the signal with our choice of how to model the system? So there's a few steps towards this. And what I'm going to build up to over the next few slides is to show how you can actually determine or bound the average of the entanglement entropies of these post-measurement states using a scheme like the one I've just described. The first step towards this is to generalize a scheme people often call classical shadows that was developed a few years ago now by these two groups. So we have a different density matrix every run of our experiment. What we'll do, we can imagine applying some random unitary It could be HAR random, it could be from the Clifford group. I should stress this isn't specific to single qubits, but I'll talk about it in that language. So we take our local density matrix, we scramble the information locally, and then what we do is we measure. We measure and we get a result ZR. Now, what we then do is you construct this kind of funny looking object called a shadow. This is not a valid density matrix, I have to stress, but it has the property that on averaging it becomes a density matrix. So this thing called a shadow is just defined such that if we were able to average over these unitaries and over these measurement results, then we would be able to wash out this fluctuation and be left with the true density matrix. So the reason I'm writing it in this way is to draw an analogy with what I was describing a moment ago in the context of washing out the fluctuations in the observed eigenvalue in an experiment. Okay, so now we can play a similar game to before. So now we can take these shadows, we can multiply them by some now matrices we choose, getting back to a similar problem to before, and on averaging in this way, we get to some information on the ensemble of post-measurement density matrices. The question is, how should we choose WM? So one quantity that many of us are interested in characterizing characterizing quantum states is the entanglement entropy. So I'll now, over the next couple of slides, show you how, using a cross-correlation between theory and experiment, you can bound the true average entanglement entropy of your quantum system. So what you could do is you could choose this matrix, these matrix-valued weights, to be minus log rho Cm. One way of thinking about this, for those who are familiar with it, is this is the entanglement Hamiltonian. So you're taking the entanglement Hamiltonian, and what you'll do is you'll take the entanglement Hamiltonian, multiply it by this shadow you extracted in your experiment. On averaging, you'll find this funny-looking object, which still clearly depends very sensitively on how you've chosen to model the system. Rho Cm is just your classical estimate for the density matrix. And so what I'll call this thing, although it's not so well motivated so far, it will be next slide. I'll call this thing the quantum classical entanglement entropy. But the useful thing about the quantum classical entanglement entropy is not that it necessarily tells us anything. So far, it doesn't appear to tell us anything direct about the quantum system. The point is that it appears as a contribution to the quantum relative entropy. And so this is where we get closer to ideas in cross-entropy benchmarking. So the quantum relative entropy is defined in this way. So this first term here is minus the actual entanglement entropy that we'd like. And the second part here is the quantum classical entanglement entropy that we're able to extract in our experiment. So the point is that because the quantum relative entropy is actually non-negative, this means that by cross-correlating experimental data with the results of our simulations, it's actually possible to find an upper bound on the true measurement average entanglement entropy. To add to this, and I'm sure I won't have time to talk about this later, you can actually also find a lower bound on the true measurement average entanglement entropy. So this really gives you a way of inferring the effects that the measurements are having on the entanglement of a quantum state without having to post-select. You just need to have some simulation. And these simulations can be done after your experiment. Okay, so the significance of this, as highlighted in bold here, is that this actually means that despite the fact you can only see each post-measurement state once, it's nevertheless possible to probe physical quantities. So there's not this game of cross-correlating between your expectation and what's really going on in your experiment is not completely artificial. Another nice thing about the fact this is a bound on a true physical quantity is it gives you the ingredients for a variational scheme that you can use to improve your models for your quantum system based on experimental data. That is to say, I could give you a set of measurement outcomes and a set of shadows, rho s, and you could then take a neural network or something much simpler and try to optimize your model for the quantum system by minimizing this average cross-correlation. Okay, so if that seems a little bit abstract, I can talk about an application I say an application, but I can talk about an actual experiment you can do in this way. And the scheme I'll describe is very similar to what was implemented in the Google experiment not long ago. So the physical setup we can imagine is you have your quantum circuit, and you're subjecting your quantum circuit to local measurements. Okay, and these are the outcomes here. So these unitary gates are acting to entangle the different qubits. These single qubit measurements are disentangling the qubits. And now we know that, and this is dual to this transition in random circuit sampling I was talking about before, if the measurement rate is sufficiently low enough, in this case, the state will remain highly entangled. That is to say, your evolving quantum state is robust to a finite space-time density of measurements. On the other hand, if you push your measurement rate too high, the state becomes weakly entangled. It falls apart and ends up being efficiently simulable. So one way of viewing this entanglement transition is really a transition between states you cannot describe in a classical computer and states that you can. So, okay, let's move back to a probe like the one I was talking about before. Let's imagine that after running this evolution for some time, we measure all these qubits in the middle. And now we can ask, having measured all these qubits in the middle, what effect does this have on the entanglement entropy of this qubit over here? That is to say, has the state fallen apart, or are we going to create a bell pair between these two sides of the system? So to check this, we can use exactly the scheme I just described, where we take one of these qubits at the edge, we apply a random unitary, we measure, we extract a classical shadow. I shouldn't call this a classical shadow because this is really the quantum side of the quantum classical cross-correlation. And the point is that for p less than pc, the boundary qubits remain entangled. That is to say, you create a long-range bell pair with some fidelity. So for p greater than pc, on the other hand, you find the boundary qubits are disentangled. But what I'm going to be focusing on over the next slide or so is the critical point itself. So really the threshold at which we can, the threshold where we're on the edge of not being able to describe our quantum system. So at this point, the entanglement entropy of this qubit actually decays as a power law of the system size. There's a kind of emergent scale invariance. And the classical memory that you'd need to store the state at this threshold, we believe is just polynomial in the system size. We can represent it with a matrix product state where the bond dimension is polynomial in the system size. So yeah, the question is now, okay, you run up against this threshold where you can no longer do simulations, and you can ask, how do your simulations behave? So just to review, we evolve the quantum state, we measure the bulk qubits, we extract a shadow. Then our classical simulation now is no longer going to be an abacus, but it's going to be a tensor network simulation at a finite bond dimension chi. As I was just saying, the memory required for the simulation is just polynomial in the system size, where beta is some exponent that I can mention in a moment. We feed the outcomes into the classical simulation. The classical simulation spits out this classical estimate for the density matrix, and from this we get our quantum classical entanglement entropy. Now, what we can do is average this quantum classical entanglement entropy and ask how good, which is our bound on the true entanglement entropy, and we can ask how good is our bound. So this is when some ideas developed maybe 14, 15 years ago now become useful. And this is to do with this, okay, if we want to ask how our simulations behave, we can appeal to some ideas from the theory of finite entanglement scaling. So the point is that if you're at a critical point, if you have some system with power law with scale invariance, then typically if you impose the constraint of only using finite classical memory, this is going to introduce some finite length scale. This finite length scale, this correlation length, I'll call psi, and it was shown back in 2009 that this length scale typically scales polynomially with the bond dimension. So that theory of finite entanglement scaling is really what it's doing here. What it's doing is quantifying the classical memory that you would need to observe quantum criticality on a classical computer. So they were thinking about one-dimensional systems exhibiting conventional quantum phase transitions, such as the one you see in the transverse field Ising model, for those of you who are familiar with that, or that also occur pretty generically in one-dimensional systems with particle number conservation, so one-dimensional quantum liquids. So I'm going to be talking about a slightly different kind of finite entanglement scaling. This isn't going to be assessing the memory that's required to observe interesting effects on a classical computer. What I'm going to be talking about is because I'm talking about this quantum classical object, I'm going to be trying to quantify the classical memory that's required to observe measurement-induced criticality on a quantum computer. And remarkably, a similar thing happens. So if you look at this quantum classical entanglement entropy, you find that it has this particular scaling form. So what I'm showing on the right here is the setup I described before, where I measure the bulk qubits. I determine I try to upper bound the entanglement entropy of one of the edge qubits, and I ask how this entanglement entropy behaves with the system size and with the bond dimension. Now, down here, we're in the kind of memory unlimited regime, where the system has not noticed that you're working at finite classical memory. Over here, you see the kind of the exact result. Your bound is very tight, and you see the expected power law decay. But then, as the constraints of a classical memory become more severe, while the true signal should keep going down as a power law forever, your bound is going to shoot off to something very large and become, a pretty poor bound. But the point is that the way that the simulation breaks down is, you can think of it as really a signature of measurement-induced criticality. So these are just some numbers that aren't super important. But so the point is that what I've done here is I've taken a number of different bond dimensions and system sizes, and by showing that there is this kind of universal collapse of all of this data, you can see that there really is a finite length scale introduced to your quantum classical cross-correlation by the constraint of classical memory. And yeah, so given that any probe of measurement-induced phenomena is ultimately going to involve a classical simulation in some way, this is a pretty sharp probe of what's going on. Okay, so that's an example of the kind of thing you can observe using these cross correlations. In the last couple of minutes, I'll just flash through a few lines on how you can also get a lower bound on the entanglement entropy. If your aim is to characterize the entanglement entropy of a quantum state, there's actually going to be a physical setting in which you can tightly determine the true entanglement entropy. So what we're going to have to, the game we're going to have to play here is extending the scope of our investigation. Let's not just look at that one unmeasured qubit. Let's think about two unmeasured qubits. Let's call these A and B. So rho M A B is the density matrix of A and B conditioned on the outcomes elsewhere in the system. And rho C MAB is our classical estimate for this density matrix. So the relative entropy of the region AB is defined in this way. Okay, I can just write it in terms of the quantum classical entanglement entropy. And by the monotonicity of the entropy, we know that this relative entropy, that is to say the difference between our, sorry, I should unpack what this means. So DABM is quantifying how different our classical estimate is from the true density matrix. And this is to say that the difference, if we throw away some of the information by restricting to just part of the system, the perceived difference will be smaller. So just since entanglement entropies are always greater than or equal to 0, this immediately implies that you can also get to this lower bound in the entanglement entropy. Combining this with the thing I described before, we have both lower and upper bounds on the post-measurement averaged entanglement entropy. And interestingly, while the upper bound here becomes tight in the limit of a perfect classical simulation, even for a perfect classical simulation, you have to be a bit careful about which physical settings you look at. So if it turns out that you've prepared a pure state on A and B, then you can both lower and upper bound the entanglement entropy. Otherwise, you have some finite tolerance set by this entanglement entropy. But okay, that sort of brings me to the end. So to summarize what I've been talking about, so I've been talking about how if you want to do an experiment studying the effects of many measurements on a quantum system, you have to change what you mean by a comparison between theory and experiment. You can't just compare your theoretical estimate with the experiment. You have to compare the cross-correlation between the two of them with your theory. I've shown that this is not a completely artificial game, because there are certain ways that you can cross-correlate that allow you to bound system properties which do not depend on the way you've chosen to model the system. And I think what's generally pretty interesting about this setting is that it appears that you can only really observe measurement-induced phenomena that you can also simulate, which raises a pretty interesting question of whether a quantum simulator actually gives us very much when we're trying to study measurement-induced phenomena. The outlook here is, okay, first off, if that doesn't turn out to be, if it turns out that quantum simulators do give you something beyond classical computers when studying the effects of many measurements, there are a number of new things we can do. We can study the phenomena like those I just described. We can study something people call deep thermalization, which is the a higher order form of what people often call the eigenstate thermalization hypothesis in quantum statistical mechanics. And something that I think would be pretty interesting that we're thinking about a bit now is whether you can use variational methods to learn, efficient descriptions of post-measurement quantum states, even in the setting where the pre-measurement quantum state is quite complex. So you can imagine taking a highly entangled many-body quantum state that you can't possibly store, measuring it to decrease its complexity, and then asking whether this classical information extracted through measurement is enough to construct an efficient model for the unmeasured subsystem. Okay, that brings me to the end, so thank you for listening. So in that regime, the bond dimension is supposed to be scaling exponentially with the system size. So let's see, just for the purely classical object or for the quantum classical object? Oh, so for the purely classical object, I mean, the numerics we've done so far indicates that, you know, as you increase the bond dimension, not much is happening because the bond dimensions you require are just so large that you're not converging. It's not clear right now. We should discuss this a bit more later, but it's not something we thought too seriously about, given that we expected all the simulations to break down there.